All right, we're going to go over Chapter 8, Section 1, which is on torque. I'd ask you right now to get your books out and turn them to page 278 and follow along as I go through this. I am going to refer to some pictures and diagrams in the book as I go through this. So why don't we get out our books and turn to page 278. All right, so what we're going to look at is torque. Torque is a quantity that measures the ability of a force to rotate an object around some axis. So we think of torque a lot of times in terms of vehicles and how much torque they produce. And all that is the force needed to turn an axle and how much force there is and how much torque it can produce. It's very valuable in terms of towing and things like that. Keep in mind though that this force cannot be on a path that goes through the center of an object. If the force goes to the center of the object, think of a force being pushed on the center of an axle, okay, or the force being pushed on the center of a basketball. The basketball is not going to rotate. You're just going to push it along, okay? So it can't be going through that center mass of the object. All right. Torque depends on a force and a lever arm. There needs to be both. And here I'd ask you to look at page 279, figure 8.2 and 8.3, and it shows a cat coming through a door, a hinged door, and the figure next to it is a picture of it. But we need a lever arm. And the lever arm is the perpendicular distance from the axis of rotation to a line drawn along the direction of the force. So if you notice in figure 8.3, it's 8.3 shows the little letter D, and that is the distance from the axis of rotation. In this case, it's the hinge, and it's to the point where the force is pushed on it. Okay, and that in this case it'd be the cat's head or the cat's nose pushing on the door. So this shows those quantities, the force being pushed on it, the distance. The lever arm is the distance, in this case, between that hinge and where the cat is pushing on the door. So a lot of times lever arm is going to have this variable D for a distance, because that's how long the arm is. We may think of a lever arm as something used to pry, and that's exactly what it is. You're rotating the lever arm around some point to pry on the other side. All right, so D is the perpendicular distance from the axis of rotation to the line along which the force is applied. And we'll take a look at more of these as we go through this. So in each example, the cat is pushing on the same door. If we look, I'm getting ahead of myself, figure 8.4 on page 280. So if we turn the page, on the top of the page there's three pictures, and it says most torque, less torque, and least torque. In each case, the cat is pushing on the door. It's just where the cat is pushing on the door. On the one all the way to the left, it's pushing right in the middle of the door. Okay, it's pushing perpendicular to the door. And as the cat is going through the door is opening, and notice where theta is there. That angle is getting smaller, and that's the angle between the force and the lever arm. Okay? So notice the force is going outwards, so it's that that angle between that force and the lever arm. Notice from the hinge of the door down to where the cat is pushing, that's the lever arm. That's the distance. Okay? So all three of these are going to have some torque, but it's producing different amounts of torque. So because of this, or because we know that these are all producing different amount of torque, the lever arm stays about the same. What's changing in this case is theta, that angle. So that's going to tell me that there is some relationship theta is involved. And if we look at the equation just below for torque, the symbol that is used, okay, and what you see is this, it It almost looks like pi with only one arm. Okay, shows a little better right here, and that's called tau. It's a Greek letter. Okay, and this measures the magnitude of torque. Remember, magnitude is some measure of torque. And we get it with this following equation. So tau, or the torque, equals force times that lever arm multiplied by the sine of theta. Now, remember the sine of theta is 1. So if it's 90 degrees, the sine of 90 is 1. So to be 90 degrees is that first picture of the cat with the most torque. Okay, it is pushing perpendicular to the door. Okay, so the cat's, that angle, the force, and the lever arm are perpendicular to each other. So torque is the force times that lever arm. Our standard unit is the Newton meter. So notice that the inclusion of the angle theta, the angle between the force and the distance from the axis. Okay, so this is the force, or the equation that we're going to use to be able to get torque. And as that door opens, it's going to change the amount of torque we have, because the only thing that's changing really is theta. So it's going to change the amount of torque we have. Torque with sign convention. Up till now we've talked about rotation. And rotation counterclockwise was positive. So when we did counterclockwise, that was a positive rotation. When I did clockwise, that was a negative rotation. This is going to work very similarly. Okay, so the sign of torque is positive if the rotation is counterclockwise. So just like before, that's positive. Negative, again, if the rotation is clockwise. So it's the same as what we talked about before. So let's take a look at an example. So imagine if maybe at Thanksgiving this happened to you. You have a wishbone from the turkey. Okay, you're pulling on it with a perpendicular force. Okay, perpendicular. So now I know that sine theta is actually sine 90, which is 1. And when that's the case, we don't have to put it in there because it's 1. You're multiplying by 1. So you're pulling perpendicular with f sub 1. Your friend is pulling with f sub 2. If it rotates counterclockwise, okay, when both of you pull on that wishbone, it's rotating counterclockwise. So we're going to have some positive value here. So our magnitude of what we're going to find, we have to get a total or a net torque. And that's what the equation down here shows. So if it rotates counterclockwise, we have a positive torque because of direction. Your friend exerts a negative torque. So let's say your torque's positive, your friend's negative. You pulled this way, your friend pulled the other way. So to find the net torque, we got to add up the individual torques. So we're going to take the force times the lever arm of whatever you pulled and add to it the force times the lever arm of your friend. And that's a negative direction, so you actually could subtract one from the other. Now, I know this force should be greater because it rotated counterclockwise. It's got to be a positive value. So let's take a look at a specific example now. A basketball is being pushed by two basketball players during a tip-off, assuming each force acts perpendicular to the axis of rotation. That's key now because being perpendicular to the axis of rotation makes this 1, and in theory, because we multiply by 1, really we can just get rid of it. So we're going to just do torque is force times distance. So assuming each force acts perpendicular to the axis of rotation through the center of the ball, find the net torque acting on the ball. Now, be careful. Some of you probably saw the center of the ball. We talked about the axis of rotation through the center of the ball. The force is not going through the center of the ball. So let's take a look at our example. This is a case where we have to get our net forces. I have to get the force of one person pushing on the ball and the force of a second person pushing on the ball. So I'm going to find torque of one, torque of both people. I think I said force. is going to be my force, 15 newtons, times my lever arm, 0.14 meters. Now, it's rotating, okay? Basketball is pushed by 2 basketball players during tip-off. We want to find this torque. The value of this, the net torque acting on the ball, we are going to get a value of 2.1 Newton meters. Okay. If you're looking at the diagram on page 281, it shows the picture of how the ball is rotating, and it's rotating clockwise, which makes this value actually negative. Now if I look at tau 2, or the torque of our second, I am going to take my 11 newtons, that's the force of the second, and 0.070 meters, and I get negative 0.77 Newton meters. Now to get my total, I am just going to combine these two, and I actually come up with negative 2.9 Newton meters. So this will be our total torque on this. It's 2.9 Newton meters. The negative shows the direction, that it is in a clockwise spin. Right. If the torque required to loosen a nut on a wheel of a car has a magnitude of 40 Newton meters, okay, so that's the torque. That's how much we have. What minimum force? Minimum force means it's going to be perpendicular to the wrench. Must be exerted by a mechanic. It's perpendicular to the wrench because that gives us the sign of 90, okay, which is 1. So what force must be exerted by a mechanic at the end of a 30 centimeter? Now our values up till now have been in meters, so we need to convert that. So what force do we need to loosen that nut? So I'm going to do the same equation. Perpendicular, so I don't need to deal with the sign of 90. So this is going to give me pi instead of tau. My force, 40.0, I'm sorry, I don't make this mistake that I just made. Our torque is 40.0 Newton meters. The force is what we want to solve for, and our lever arm is 0.300 meters. Now to solve for force, I'm going to divide by my 0.300 meters. These will cancel. 300 meters. Meters cancels. Now look what I'm left with, newtons, which is appropriate for force. So my force is going to equal 40 divided by 0.3, which is 133.3 repeating, but with our significant figures, is 133 newtons total. So the assignment I want you to work on now is page 282 in your book, questions 1 through 5. This is the section review questions, not practice 8A, the section review.